Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video, we are going to discuss about the design of tension members. In this video, we will cover introduction to tension members, limit states for tension members, nominal strength of tension members, gross area, net area of section, effective area of section, shear lag factor, AISC specification for design of tension members, capacity analysis of tension members, and design procedure. And finally, we will solve one design example. First of all, tension member. So steel tension members are the structural elements that are subjected to direct axial tension load, and they tend to elongate under the application of tensile force. So tension members are probably the most common and most efficient member in steel structures. So they are found in plane as well as space trusses like this. Here the members of truss may be in compression or in tension. Similarly, they can be found in the transmission towers. So here some members will be in tension and some member will be in compression. Similarly, wind bracing can be a tension member. For example, here wire is used as a bracing, so this will be definitely in tension. So here in this case, it might be in compression as well as in tension. Okay, next is common shapes used for tension members. So many shapes can be used for tension members. So out of this, the most common are round bars. So we can use this round bar or wire as a tension member. We can use flat bar. We can use angle, single angle or double angle. We can also use the double angle in this shape. Channel section or double channel section, lattice channel section, W section, I section or S section, and built up box section. So many sections or different possibilities are there to combine these sections to get the good results in case of tension members. So structural T's or T sections are mostly used in case of light structures for the chord members, bottom chord or top chord members of truss. We can use T section. Similarly, I section, channel section or built up section. So W or I section, channel section or built up section. So these sections can be used where the larger rigidity is required. So where it is required that the deformation should be minimum or the deflection should be minimum, sagging should be minimum, in that case we need to use I section, channel section or built up section. So rods or bars, in case of bracing we can use bars, wires or rods. Similarly, wires are used in case of gay wires in suspension bridges. So in case of suspension bridges, to support the deck we use these wires. Okay, next is limit states for the tension members. First, we need to understand what is limit state. So limit states mean, or it define different failure modes. So when we say limit state, it means it relates to some failure modes. The failure modes of member are connection. The strength of each limit state can be determined from the mechanism of failure mode. So based on the mechanism of failure, we can calculate the strength corresponding to that limit state. So if we recall, in the first chapter, we have discussed the objective of design. In the objectives of design, we have studied that our structure should be like that it should not fail either in strength, rigidity or stability. So we need to avoid all those failures and our structure should be capable to resist the applied loads. So first we need to investigate what type of failures can occur in a structure or in a structural member, and then corresponding to those failure modes we need to design. We need to make sure that our structure should be safe against those type of failures. So in case of tension members, there may be 5 or 6 different type of failure modes that can occur. So limit state are failure modes for the steel tension members. So in case of member limit state, there could be tension yielding. So we will see one by one what are these limit states. In the connection, there might be tension rupture, block shear, bearing or tear out, and bolt rupture. So these type of failure can occur in case of a tension member. So let's discuss all these limit states one by one. So first of all, tension yielding. Tension yielding. So tension yielding occurs when the stress on the gross area of a section is large enough to cause excessive deformation. So first thing, the tension yielding will occur in the gross area. So in the gross area, if yielding occur in that portion, we consider it as a failure, and that will be termed as tension yielding failure. So in that case, there will be excessive deformation in the member, and that deformation will be considered as failure. If we recall, in case of rigidity failure, we discussed one example that in case of beam, if the deflection is excessive, we considered it as a failure. Similarly, in case of tension member, if the deformation is excessive, then we consider it as a failure. So here we need to note that yielding in the net section is not a failure. So yielding at this position at the connection is not a failure, but the yielding in the gross section is a failure. Why? Because the net section is limited in length, and hence elongation due to the yielding may not be excessive. What it means? For example, the applied load on this member is such that this member has reached up to its yield strength, or the stress in that member has reached up to yielding Fy. So technically, all the member, every point of the member will yield. But if we consider the deformations, so this much portion where we have the gross area, here the length is larger, so the deformation in this portion will be too much or excessive deformation. For example, if this length is 2 meter and the deformation is 1%, so here 20 millimeter deformation will occur in this portion. And in this area, if this is 200 millimeter, the total length is 200 millimeter, then in this much portion there will be only 2 millimeter deformation, and this 2 millimeter deformation is much smaller as compared to this 20 millimeter deformation. So we will consider this elongation or this area, the yielding in this area, as a failure, but the yielding in this portion we will ignore that. Why? Because the deformation corresponding to that yielding are not that much high. Okay, so if we see in this figure, so this is our gross area, so here there will be yielding. So yielding will be over here, and in case of tension yielding, we need to consider the whole area while calculating the strength corresponding to tension yield limit state. Okay, next is tension rupture. The tension rupture is critical in case of these connections at the net area. So the tension rupture occurs when the stress on the effective net area of the section is large enough to cause the member to fracture. So when the stress in this section reaches Fu, if we see the stress strain curve, we have curve like this. So here we have yield strength Fy, and here we have Fu, ultimate strength. And when a section reach its ultimate strength, so after that it will rupture. It will fail, just like a crack will appear and it will fail. It will change, or it will convert into two pieces. So rupture failure will occur when the stress is large enough to cause the fracture, so which usually occur across a line of bolts. So this occurs across the line of bolts, either in this direction or either over here like this. So here if we see, here it is along this line of bolt. Okay, so we can see this picture here. The failure is along the line of bolt, from the line of bolt here as well. Okay, so the question is how this failure occurs. So for that we need to understand a concept from this figure. For example, we have a plate and we insert a bolt in this hole. So when we apply the force over here, so in this plate, in the surrounding of this bolt, there will be tensile stresses. And these tensile stresses will have the higher value or the highest value near at the edge of the hole, and this stress will continue to decrease away from this hole or away from this bolt. So when we go on increasing this load, so this stress will go on increasing. A stage will come when this stress at this point will reach to Fy. So here it will reach to Fy, sigma Fy, the yield strength of this plate. And because of this yield stress, the material near to that or at that location will yield and it will deform. And then the next fiber will reach its yield strength, and then the next, and this will continue. And the previous fibers will continue to deform. A stage will come when the first fiber that have yielded first, it will reach its ultimate strength, sigma u or Fu. So when this fiber will reach at its ultimate strength, so instead of further deformation, there will start fracture. So that fiber will fracture. And then the next fiber will reach its ultimate strength, and then the next. And as these fibers go on in reaching their ultimate strength, the fracture will continue to propagate in this direction. So if here is a hole, so first the first fiber will fracture, then the next, and in this way the fracture will continue to grow from hole toward the edge of the member. So this type of failure occurs when the stress inside the member reaches its ultimate strength of that material. Okay, next limit state is block shear failure. So for some connections or some connection configuration, the tension member can fail due to tear out of a material at the connected end. If we see the figure over here, so this much material has been teared out of this plate. Similarly in this figure, so this much material has been teared out of this material. So this is called block shear. So this type of failure is termed as block shear. It happens as a combination of shear and tensile failure. So in that case, in case of block shear failure, it is necessary that there should be a combination of shear failure as well as tension failure. So if we see this first case here, this much portion along the line of the bolt, there will be shear failure or shear rupture, and in this portion perpendicular to the tensile load, there will be tensile rupture. So this combination of tensile rupture as well as shear rupture is termed as block shear failure. So this is similar to this figure. This is an actual figure showing the block shear failure. So similarly, the other possibility is that along the one line of bolts there is shear, and on this portion there will be tensile rupture. Or it may be opposite to that, on the bottom side there is a shear along the bolt line, and on the upside there is a tension rupture. So if we consider this figure, or if we see this figure, so here along this line there is shear rupture, and on this line here is tensile rupture. So this type of failure is termed as block shear. Okay, next limit state or failure mode is bearing failure. So if we apply a load on this bar or a plate and the bolt is present over here, so the area of this plate which is in contact with the bolt, so that will come under compression. So here we have a bolt, for example. So area just adjacent to that will come under compression if the tension load is in this direction. And because of this compression load, the material can yield. If this plate yield at this location because of compression, so such type of yielding is termed as bearing. And we considered it as a failure because of compression yielding, and that is termed as bearing. So if we see in this figure over here, so the material at this location has yielded under compression, so it is termed as bearing failure. So this type of failure is possible in case of pin connections. If we have two plates and these are connected with one bolt, so in that case this type of failure is quite possible. Okay, next is tear out failure. So it is similar to the block shear, but in case of block shear we have shear failure or shear rupture plus tension rupture or tension failure. So but in case of tear out failure, especially when the connection is a pin connection, we have a single line of bolts or single bolt. So in that case the material can rupture along the direction of this applied force at the edges of this bolt. So and this much portion of the plate can tear out of this plate. So such type of failure is termed as tear out. So we can see in this figure over here. So if we see this figure, so here because of the load, so fracture has developed in this direction, and if we continue to apply the load, so fracture will continue in this direction, and this much portion of the plate will tear out of that plate. And here is the actual figure. So here if we see this much portion has been teared out of this plate. So this happens mostly when we do not provide this edge distance, adequate edge distance. If the edge distance is not adequate, in that case tear out failure can happen. Okay, the next possibility or the next possible failure is bolt rupture. So we can see such type of configuration if we have two plates and we join these two plates with the help of one bolt. So in that case, here the load will be in downward direction and here the load will be in upward direction, and the bolt can shear at this location at the surface of these two plates. So here the force will be in upward direction and here the force is in downward direction. So this at this section it can shear. And if we have a single plate on one side but double plate on the other side, and then these are connected with the help of bolt, so in that case there are two surfaces which can go under shear. So one surface here and one surface here. So these two surfaces can go under shear rupture. So this is termed as bolt rupture or bolt failure. This might be critical in some cases, especially in case of pin connections. Okay, next is design strength of tension member. So we have studied the possible failure modes in case of tension member. Then the next is design strength of tension member, and that will be based on the possible failure modes or possible limit state. The strength of a tension member is controlled by the lowest of the following limit state. So for example, in a tension member there may occur three types of failure: tensile yielding, tensile rupture, and block shear failure. So we need to investigate the strength of that member corresponding to these three types of failure, and the lowest out of these three will guard, and that will be considered as the design strength of the tension member. So in case of structural shape or tension members, when the connection is not a pin connection, so in that case the three conditions or three type of limit states are critical. First one is yielding at the grass area, the second is failure at the net area or the rupture, tension rupture at the net area, and the third is block shear. So we need to consider the strength corresponding to these three type of limit states. So if we talk about the first limit state, which is yielding of the grass area, so in that case the nominal strength is given by Fy Ag. So we need to understand from where this equation comes. So we know that if axial load is acting on a member, in that case stress is equal to sigma is equal to P over A. If it is a compression load and if it is a tension load, then we can write sigma is equal to T over A. And if I rearrange this equation, so T is equal to sigma times A. So this is here if we see, this is a stress under the application of this applied load. But here we want to calculate the maximum capacity of this section, or the maximum load of this section that it can resist. So the maximum capacity will be considered if we are considering yielding. So in that case, the maximum capacity will reach if the stress in this member reaches its yield strength. So when this member will reach its yield strength, the load corresponding to that will be considered as its maximum capacity corresponding to yielding. So here in this equation, we can replace this T with Tn, which might be the nominal tension load that it can bear, and sigma will be replaced by Fy, the yield strength of that member, and A is the gross area, total area of the section. So this equation will become Tn is equal to Fy Ag. So we have replaced the stress with the maximum possible stress in that member at failure, and A with the gross area, and the load, tension load, will be the maximum load that this member can resist corresponding to yielding or yielding failure. So from there we can get this equation Tn is equal to Fy Ag. So this is the nominal strength. If we want to convert it into design strength, then we need to multiply it with the factor 0.9 in case of LRFD design method. So this is strength reduction factor 0.9 in case of tension members when we are considering yielding. So the next limit state is failure or ultimate strength on the net area, or we can say the limit state or the strength corresponding to tension rupture. So the rupture will occur when the stress in the member reaches up to the ultimate, this value. Yielding occur when the stress in the member reaches to Fy, and the rupture will occur in the member when the strength in the member reaches to Fu, the ultimate strength. Okay, so we just need to replace, in this case, T sigma is equal to A. We just need to replace this sigma with Fu instead of Fy. And Ag, and as we have seen that this fracture is common in case of net area or effective area at the section where we have bolts or holes. So instead of gross area, this gross area, we will consider this net area or effective area. Effective area at the connection which is resisting this applied force. So our equation will become Tn is equal to Fu times Ae. Fu is rupture strength and Ae is effective area which is resisting the applied load. And the design capacity corresponding to tension rupture will be, if we consider the strength reduction factor equal to 0.75. So in case of rupture, the strength reduction factor is 0.75, and in case of yielding, strength reduction factor is 0.9. So we need to keep this thing in mind. Whenever we say that in case of steel there is a yielding, so we will consider 0.9 as a strength reduction factor, and if it is a rupture, we consider 0.75 as a strength reduction factor. So no need to memorize these equations, so we need to just understand the basic concept that it is a rearrangement of the equation P is sigma is equal to P over A. So here AE is the effective area which is equal to U times AN. AN is the net area and U is the strength reduction factor, reduction factor, or we term it as shear lag factor. So we will study the detail of this gross area, net area and shear lag factor in the next slides. Okay, next limit state is block shear failure. We need to consider the strength corresponding to block shear failure. So as we have seen earlier that block shear failure occur when tension rupture as well as shear rupture occur simultaneously and some portion of the connection is teared out of the member. So this type of failure is common in case of thin plates. If plate is thick, in that case there is very less possibility for block shear failure, but in case of thin plates where the thickness of plate is less, so this shear failure might be critical. So here failure is a combination of tearing, means shear rupture, plus tensile rupture. So if we want to calculate the strength corresponding to block shear failure, so in that case our nominal strength will be equal to strength corresponding to shear rupture plus strength corresponding to tensile rupture. Okay, so first we need to understand, we can simply write for this one strength corresponding to tension rupture. So it will be equal to Fu times ANR AE, effective area, sorry, in case of this we will have only net area, not effective area. So when we will study the concept of effective area, then this will be clear to you. So strength corresponding to tension rupture will be equal to Fu times An, and strength corresponding to shear rupture will be equal to Ta, means shear strength, times the net area, right? So now we need to consider what will be this shear strength of the steel. So either we can calculate or we can determine the shear strength of steel. So if we know its shear strength, then we can directly input that value, or otherwise we can approximate this shear strength of steel. So after a sufficient test, we have determined this combination, which is shear stress of steel is equal to 0.6 times Fu in case of rupture. Means 60% of the rupture strength will be equal to the shear rupture strength. So shear rupture strength will be equal to 60% of the ultimate or rupture strength of steel in tension. So we can replace this tar with 0.6 times Fu and then An plus Fu times An. So this will be our strength corresponding to block shear. So here if we see in this equation, in equation 1, so we have 0.6 Fu times A and V. So net area in shear, Fu is the ultimate strength and 0.6 is actually, we have the yield shear strength 0.6 Fy and ultimate or fracture shear strength is equal to 0.6 Fu. So 0.6 Fu is equal to actually Ta ultimate. Okay, plus U time Fu time An, and this is Fu time An is equal to actually tensile rupture strength, and this factor U is actually a strength reduction factor. So if this much area which is under tension, if it is equally stressed, the stress in this much area is same, the tensile stress is same, so in that case we considered its value 1. But if this much portion is not subjected to uniform or equal stress, in that case we need to consider its value less than 1, for example 0.5. So why? For example, we have a plate and it is subjected to such type of load or eccentric load, so this much portion is stressed more, here the stress is more, but on this side the stress is less. So when we keep on increasing this load, the stress will keep on increasing and this side will rupture first, and then this rupture will continue to extend in this direction. So at the first stage the whole section will not be resisting the applied load. So as a result, the strength of the section will be less as compared to the strength if the load or the stresses on the whole section are constant. So normally in case of block shear it will be considered as 1, because as we have seen the previous cases over here this much portion have constant stress, here we have constant stress, here we have constant stress. So in all these cases we will consider its value 1, the factor U will be considered as 1. So this is how we can calculate the block shear failure in case of tension rupture as well as shear rupture. So according to AISC code, it considered only the rupture, but some authors considered the shear yielding as a failure. Tension rupture plus shear yielding, they considered it as a failure. So if we consider the shear yielding as a failure, so then the strength will become 0.6 Fy, mean instead of Fu we will consider Fy because we are considering yielding, and the net area in shear will be changed to net area will be changed into gross area in shear, and this factor will remain same. So here the question is how much will be the net area in shear and net area in tension. So for that we can see over here, if we have the failure like this, we plate and we have the bolts like this, and failure occur in this direction. If up to here we have a section, so failure will be in this much portion. So here will be in this portion there will be shear failure, and in this length there will be tension rupture, and here it will be shear. So if we see from here up to here, we have two holes or one hole and half hole in this failure path. So while calculating the net area in tension A and T, it will be equal to this much length from here to here. For example, I say it is L1. So L1 minus, we need to consider or we need to subtract the diameter of this hole. So we need to subtract 1.5 times diameter of hole. Half from this, from the center of the hole, and for this hole it will be considered it complete. So this will be our net area multiplied by thickness of the plate. And in case of shear area, net area in shear, so in that case again we need to consider length from here up to here. For example, it is L2, so L2 minus the diameter of this hole and the diameter of this half hole, again 1.5 times diameter of hole, and then we need to multiply it with the thickness. And if the situation is like this, we have holes over here and the failure is like this. So we know the distance between the center of the holes, for example it is equal to L1, then we need to subtract, to get this much distance which is under tension, we need to subtract the half diameter of hole from here and half diameter of hole from here. So this much length will be actually equal to L1 minus diameter of hole, half from this side and half from this side. And for this side, the area which is under shear, so we know this distance up to this. So from the center of the hole, if we know the distance from the center of the hole and it is L2, then we need to subtract L2 minus diameter of hole H1 and minus 1 by 2 times diameter of this second hole H2. So in this way we can consider the net area, and the area in shear will be twice of this because this area is also in shear and this area is also in shear. So we need to multiply it with 2 times of T, or 2 times this area, because two areas are in shear. Okay, next is gross area. So we will discuss this in the next video. In the next video we will discuss about the gross area, net area as well as effective area.